we see here if we would use with 5 terms only, or precision using 5 terms, so we just go here with this 1, 2, 3, 4, 5. We would not get very good results, so I want to generate just one cycle of the sine wave, but using 5 coefficients, and it starts kind of a sine, but it explodes. The less coefficients you go, the faster it explodes. If we increase the coefficients, we get a better approximation of the sine wave. But of course, if we deal with higher numbers, so suppose I want to have 2 cycles in the same amount of coefficients, then it already explodes. So one solution for this, what we can do is optimize even more. And what we are doing here is that we will just generate the positive part, and the negative part will just toggle the sign. So now here I'm using 11 coefficients and trying to do 2 cycles. Now I will have 4 cycles and 5 coefficients, and we see we have a nicely sine wave, because we are just regenerating this part, and then we copy this part with inverted sign, and then we generate this part, and so on. And this we can go indefinitely as many cycles we want. So for the duration we want of the sine wave, we are not generating the numbers, we are generating just the first cycle, and then we are repeating itself. And we see, for example, if we go with less coefficients, we start to see these problems. So right, these experiments, we see that if we use 5 coefficients, 5 terms, we get a good approximation of the sine wave that we could use to generate our sine function. So this is just an example. We used these 2 types of optimization. So we implemented this one, and then we have these very high numbers for the factorials. We've seen we can also implement this one. Then we have less problems with overflow of our data structures, and we see that we can optimize, and we could go even further. Instead of optimizing the half cycle, we could go for 1/4 of the cycle, and here we would mirror and then invert and mirror, and we could maybe go and use even less cycles.